we're going to talk a bit about science. And don't groan, science is fun. Anyway, science is the basis of almost everything. And there seems to be a lot of distrust in science these days. People are maligning science, scientists, archaeologists, and I should have put geologists there too because we're just as bad. Anyway, we need to get back to some basic truth, and everything leads back to science. You know, everybody has an opinion, but not all opinions are correct. Again, you need to follow the trail back to science. A little due diligence goes a long way. For example, here are the stairs at the Temple of Hathor at Dendara. They are commonly referred to as melted granite stairs. In truth, they are worn sandstone stairs that have had concrete poured down them in the 1800s. But the granite label still prevails because people want them to be melted granite stairs. This is the schist disc. We've sort of encountered this before with Brian too. This is not made of schist in spite of the title. Schist has a one-directional strength profile, not two. Schist would not support structures like this with the curves. It would just collapse. This is a metasediment, a metamorphic siltstone. It's close to 100% silica, which makes it very hard, which is why it was chosen for crafting intricately fluted objects from the same material. You see a lot of those in the old museum. This is the Ben stone, and it's reported to be made of a material not found on Earth. Well, at the front, here I'll get my little, hopefully this out. Here at the front, here is a little streak of some pink felspar. This is a mafic, and mafic means the dark minerals. It's a mafic-rich granodiorite, so it was found on Earth. They just chose it because it was so beautifully dark. So if we apply some scientific proof to things, we will be much further ahead in figuring out where they came from and how things were made. We can't just make things up. So let's jump into some mathematics. You know, mathematics are the basis to science. It can be traced back to prehistory when man found ways to count. In ancient times, the simplest mathematics was counting, pebbles for counting, tally marks on wood or bone. As time progressed, the realization of 2 + 2 = 4 came about. That is a non-negotiable scientific fact. 2 + 2 is never 5. Eventually, mathematical operations became essential in all kinds of transactions: trade, stock-taking, taxes, dimension of land. The Sumerian tablets included symbols denoting quantity, as did the Babylonians. And the Babylonians also used a positional number system. A value of a number is indicated by the symbol and its position. And for example, I put here 100. If the decimal point was not there, it could be almost any number around. But from Egypt, the Rhine papyrus in the British Museum is more than 3,500 years old. It includes 84 problems involving arithmetic, algebra, geometry, and measurement. The earlier Moscow papyrus shows techniques for working out areas, proportion, and volumes. So mathematics and science go way back. Now let's look at some practical mathematics. Here's a square. A square corner is always a 90-degree corner. The mathematical formula for this is non-negotiable. This is a set square. The a squared plus b squared equals c squared always will give you a square corner, a 90-degree corner. Now here's the box in the Serapeum. We saw one of these today. It displays square corners on the bottom. It displays square corners on the lid. Also, just to show off a bit, they put a trapezoid in here as well. And a trapezoid is 2 parallel sides and 2 sides not. So whenever these were made and whoever made them, they were made by somebody who understood science. Now here's the inside of the box. You've got interior square corners as well. As Brian said, they may be rounded, but they're still pretty square corners. The Syrian at Abydos, rectangular granite slabs. These are square corners on it, and this was put together with square corners as well. They knew science. The shrine on Elephantine Island, look at the corners on that. I mean, those are just precise corners. This is on the Great Pyramid, and there's Brian standing there in front of just a perfectly squared rectangular box. Now let's look at a circle. We all know that if you put something in the middle of a middle here, or right here, drag a string out to the end, spin it around the thing, you'll end up with a circle. That is still basic science. Now, here's Naphtali, a stone circle. It's now at the Nubian Museum in Aswan rather than where it came from. But still, they knew how to build a circle. This is under the step pyramid at Saqqara. Objects were made out of metamorphic gneiss, possibly a gneissic gabbro, which would account for that greenish color on there. This is from west of Abu Simbel. These are very hard stones. And, as I mentioned to some people today, that circular base appears to be lathed. You know, there's thousands of rock dishes and pots were found underneath the step pyramid. They're very old and seen in museums around the world, but not much is ever mentioned about them. Here is one of the dishes, or the whatever they are, in the Dublin Museum. Here's another one. We saw this in the Saqqara Museum today. Another circle, an allometer at Kamumbo. And this wretched looking poor little pyramid has a beautiful semicircular ceiling in there. Like, quite amazing. They knew that. They knew the science. So all sciences incorporate math. And science is not always dependent on math formulas or repetition of results. It can be observational as well. One white cow in a herd of black cows is an anomaly only until you see the neighbor's herd are all white cows. And there they are. This one actually is more science. This is a purebred Black Angus, and this is a purebred Murray Grey. It came about from a wonderful science. So there's 5 main parts of science. There's astronomy, physics, chemistry, biology, and earth sciences. And mathematics is part of it all. So let's start with astronomy. Why would astronomy be important to people in ancient times? Events in the sky were thought to reflect events on Earth. The sky could be as simple as a way of telling time or an indication that something of importance was going to happen. The sun, here is telling time. This was in Scotland, and you can see clearly from here that it's just after 1 o'clock. In addition to time, they knew the cycles of the sun. Here is the equinox, the solstice, etc. They knew all these things. And here is a winter solstice at Karnak, and picture courtesy of Patricia. Now, here's an interesting one too. This is not too far from where I live. This is a medicine wheel. It's estimated to be over 5,000 years old. It has sun alignments, including the solstices, and moon alignments. It's said to rival Stonehenge. Now, the moon, we know they knew orbits, the cycles of the moon. They also were quite aware of solar and lunar eclipses and often considered omens or signs of divine displeasure. Here are some solar eclipses. And this is a photo of the blood moon that was just happened in March this year. But does anyone ever think about the clouds? What about the clouds? Clouds often represented divine powers and connection between heaven and earth. Now, if you were out in the middle of nowhere, no lights, anything, what would you think about this little slide I'll play for you? If I can get it up here. There you go. That's in the dark of night. You don't often get lightning like that with the clouds. Yep, there it goes again. Okay, these are mare's tails. They indicate rain is coming. They don't often fail at that. This is a roll front, and it means very, very strong winds. This is out in my backyard, and if you don't tie things down, it will be in the next county. This is also in my backyard, and this is a supercell thunderstorm, and it's usually associated with persistent rotating updrafts. And I think everyone knows what that means, but we don't get very many tornadoes. So luckily, but we do get pretty nasty little storms. And I think a lot of us, especially from the Americas, we all know the little saying, red sky in the morning, sailor's warning. They knew all these things. And we'd forget about the aurora borealis because so much of the world does not see them anymore, probably because we do not have dark skies everywhere. This is in my backyard. Again, it's a aurora borealis is caused by solar winds reacting with Earth's magnetosphere. Observe can you see the Big Dipper in the background of the picture? That's pretty cool. This is also in my backyard, and this is looking straight up. I get a lot of aurora, but the aurora was surrounded by numerous beliefs. Surrounding the aurora, my lips are going faster than my brain. And they're usually not good ones. The Inuit believe that the souls of the dead dance in the aurora. The Greeks and Romans simply associated with them the goddess of dawn, Aurora. But there's a superstition that says you should never wave, sing, or whistle at the northern lights. It was believed to do so would lure body-snatching demons from the sky. Here is a comet. This is, again, in my backyard. This is the comet Atlas in October of last year. In ancient times, comets were observed and recorded. They were often attributed to divine omens or signs of things to come. Now, just quickly through the stars, Egyptians knew all about the stars. They named them, and they have a few names that in modern times we are still unsure which star they were referring to. They also named constellations. This is a depiction of constellation in the tomb of Seti I in the Valley of the Kings. And as Jocelyn mentioned earlier, we've got Tauret in here as the Big Dipper, and the crocodile is representing Draco. And of course, we've got the zodiac in the first court at Dendara, as well as the circular zodiac on the second floor. In ancient times, was astronomy or astrology the same thing? Of course they were. There's just no doubt about it. You know, the constellation of Orion the Hunter and his companion Sirius the Dog Star, they represent the heliacal rising. The heliacal rising of Sirius was observed in all parts of Upper and Lower Egypt. And what was the heliacal rising of Sirius? I think Jocelyn sort of mentioned it earlier today, and that was a fairly good depiction of what it is. Here is the constellation Orion and Sirius. This is in 36 degrees north. You can see how tilted it is. Here's in 51 degrees north, and it's straight up, and here's Sirius again. Now, Sirius, the heliacal rising of the star Sirius in Egypt, amongst other things, coincides with and predicts the time of inundation or flooding of the Nile. That sets the time of planting. That was very important to everyone. Now let's talk a little bit about physics. What exactly is physics? And basically, I'll just sort of read this first little bit. It's the study of how the universe behaves. And there's numerous different types of physics. There's thermodynamics, astrophysics, nuclear physics, optics, mechanics, quantum mechanics, classical mechanics, electromagnetics, and relativity. Now, for an example, I want to talk to you about an AFMAG EM survey. Most people have never heard of one, but it's an audio frequency magnetic electromagnetic survey. And the survey is done using natural atmospheric electromagnetic earth currents alternating at low frequencies, which are thunderstorms and other weather-related phenomena. A receiver is used to detect the interference between the electromagnetic noise and the atmosphere and the presence of a subsurface conductor, such as an ore body. AFMAG surveys were carried out on foot from the 1950s till sometime in the 1980s, and the technology now is almost all airborne. And I did one of the on-foot surveys when I was young. The survey is done by measuring with a metal rod the interference between weather activity and underground ore bodies. Does that not sound a lot like dowsing? You can maybe see where I'm going with this. There are numerous aspects of science that are no longer considered science today, but are still very much science. Dowsing is just a form of physics. Here is how they used to dowse with a willow stick. Here is a more modern one. When I was young, we used to just take a metal coat hanger and bend it, and away we'd go. I've doused in a couple of my own water wells at home, and the fellow that came to check it before they drilled it, he had this huge log attached to a rope over his shoulder, and when it started bobbing, he knew he was over the water. So there's all sorts of ways, but that is still physics. So then what is seismic exploration if not a form of dowsing? Here we've got a blast, and this is something that Brian mentioned too about the depth of how you're visioning things underground at depth. Even with the blast, you're not going down all that far, but as it reflects off of a surface, these are the detectors are dowsing rods, basically. And here with thumping a fiber-sized truck, it thumps on the ground and reflects back up. This is still, the geophones are dowsing rods. So both seismic and dowsing, in both seismic and dowsing, wave propagation is used to observe, detect, or manipulate a wave type to observe something that is not visible to the naked eye. Wave propagation can also be verbal. Om. Research suggests that chanting healing mantras can stimulate changes in the brain by helping to synchronize the left and right hemispheres of the brain by promoting alpha waves. How about a Gregorian chant? This can help reduce anxiety, lower blood pressure, and help with speech fluency of stroke victims. It positively charges the central nervous system and the cortex of the brain. Sound healing. Sound healing utilizes various sounds and vibrations from singing bowls or gongs to promote relaxation, reduce stress, and improve physical and mental well-being. Here's some modern examples: ultrasound imaging. And for healing, sound-based vibrations can help heal arthritis and a whole host of other things. Now, chemistry. Most people don't associate chemistry with, they used chemistry a long time ago, alchemy. Ancient forerunner of chemistry. All of the sciences had ancient roots. Alchemy was based on the transformation of matter, such as metals into gold or magic elixirs. And here again is sort of all the different branches of chemistry here, but I'm just going to talk about one. Copper tools. Here are some copper tools. These are from Abu Sir, just an example of them. And here's a little map of where copper is found, mainly in the Sinai, but some into the Eastern Desert. But specifically copper in desert, copper in Egypt, not the desert. Well, it was the desert too. It was found that in the 1970s that mostly all the copper tools in Egypt had a percentage of arsenic in them. The source of this arsenical copper is mainly the Sinai. The arsenic is naturally occurring in the copper. The large percentage of arsenic in the copper makes the copper stronger. This was known as arsenical bronze, even though it was a copper, and it was used until the Middle Kingdom when tin bronze was actually used. A study done at the Cairo Museum showed an Old Kingdom copper vessel that contained a higher arsenic content than just melted arsenic copper ore. It's believed that this is an indicator that the knowledge of adding additional arsenic to copper was known to increase the strength of the copper in the Old Kingdom. Based on a piece of a crucible typical of a Middle Kingdom was found in Lower Nubia. It revealed a very arsenic and nickel-rich copper. The alloy looked like it was a smelting slag. The conclusion was that the site was used for smelting a very rich copper arsenic alloy, not just melting down the native copper. They were using chemistry. And biology, I'm not really going to go into the biology, but just to let you know that it includes mummification practices, knowledge of the human body, and herbal remedies. The Egyptians knew science. Now we're going to jump into the actual rocks. So first thing we're going to do is look at some rock types. The yellow, orange, and green are all sandstones on this map. The purple is limestone, and the red is igneous rocks. But note on the purple, note how far down the limestone goes. Limestone is almost always formed in water. Keep that in mind, oceans or seaways. Now, I've lumped these into 3 different categories: the limestone and sandstone together, the granite and diorite together, and the basalt. Now, the limestone and sandstone, they are sedimentary rocks, which means they were formed by mechanical erosion and subsequent lithification, which means they were hardened into a rock of existing rocks. Or in the case of limestone, they can also be from a chemical precipitation. Now, the granites and the diorites, these are igneous, but they are intrusive plutonic rocks. Which means they are formed underground in a magma chamber. They depend on the rate of cooling of the magma underground to form a variety of crystal sizes. The basalt is an igneous, it's an extrusive volcanic rock, which means they were formed in association with a volcano. In Egypt, it's kind of an oozing kind of a lava rather than explosive. They are found associated with faulting mainly, and because of quick deposition, the lava they display is a very fine crystalline size. Now, back to the limestone. Like I said, look at how far down this limestone goes. It goes almost down into Sudan. Now, during the Cretaceous, this is the Earth during the Cretaceous, this is the Tethys Seaway where the Mediterranean should be, but the Tethys Seaway was open from the Atlantic into the Pacific. But look in particular at the top of the north end of Africa. It was underwater. And that is why we find whale bones, seashells, and all sorts of things in there. It's not just really a mystery. It was very logical geologically. So limestones, here's the middle pyramid. The pyramid itself was built mainly with nummulitic limestone, which we saw the other day, and the cap is a finer white Tura limestone. Now, the ground and the Sphinx are all limestone outcrop, and in the foreground, the Sphinx temple is made out of limestone blocks again. Another example here is Abu Rawash, and this is kind of an interesting one because the center of Abu Rawash is a limestone outcrop. It is not made out of blocks. This is outcrop. The limestone blocks were cemented on here. Do you see the pinky orange? That is all a cement that they've glued this onto the side of the outcrop, which is kind of interesting, but the cement too is made out of limestone. Now the sandstones, I've got all of them here. They're different types. Some are supposed to be fluvial and things, but the sandstones in Egypt, they also will include very fine-grained and conglomeratic sandstones. Now, here is Abu Simbel. This is carved into a sandstone outcrop. Here's the Temple of Isis on the island of Philae. Beautiful, and it's all made out of sandstone. And this is kind of an interesting one. This is Seti 1. The flooring and all the walls are made out of limestone, but all these pillars are made out of sandstone. Then on to the igneous. The red is igneous, mainly plutonic. But metamorphic rocks are created when the hot magma touches limestone or sandstone. The limestone turns into marble and the sandstone turns into quartzite. The metamorphic rocks are rocks that have been subject to intensive heat and or pressure. Now, I thought this was an interesting diagram just to indicate if it came out the top, it is a lava, it's igneous. These are the rocks commonly found in Peru, not these ones. These are all coming from the magma chambers, and this is what is found in granite, or in Egypt as granite and diorites. Now, naming igneous rocks is a challenge. Granites are named by their chemical composition. A typical granite has 45% quartz. Egyptian granites have about 5% quartz and are called syenites. So when you hear the term syenite, you automatically know sort of what its chemical composition is going to be. It's going to have very little quartz in it. There's over 600 types of granites depending on their chemical composition. Try and keep track of that. Now, it's said that all granite comes from Aswan, but some of the granite appears to be of a better quality than others. I think there's two types of granite, one from Aswan and one possibly from the Eastern Desert. And there's two types of diorites, one from Aswan and one possibly from the Eastern Desert. I've been searching for the longest time for any kind of a geological paper written on it, and I finally have found one, but it doesn't really deal with the fact that these things actually come from here, but I think this sort of is indicating to me that I'm on the right track. Anyway, this diagram illustrates the fact that there are two types of granite, the older one and a younger one. The black being the younger one and the speckled one being the older one. And look at here at Aswan, these are all younger ones. Now let's have a quick look at the ones from Aswan. Here is, I call them Aswan pink granites. And here is the unfinished obelisk. But if you look at this, these are crumbling. This is not a grade A quarry. This is probably not even a grade D quarry. Anyway, if you look on the edges of the Nile, look at the boulders. They are eroding. They're eroding very severely. They're almost rounding. And this large boulder, I thought this was quite an interesting boulder. It's across from the island of Philae, but the way it's flaking off like this, it's a very technical geological term called onion skin exfoliation. But for an example, here's at Karnak. These are both pink Aswan granites, and look at the weathering on these. And whatever is making these weather, they are weathering very badly. So now let's have a look at the older granites, these crosshatch ones from the Eastern Desert, and I think this is where the more competent granites do come from, not from Aswan. Here is, I call this a deep rose syenite. This granite is lining the king's chamber. It is a very, very competent granite. Here is a granite box in the Serapeum. Same thing. These things are very competent rocks. Oh, there, I skipped past one. The granite blocks in the Osirian, same things. There's a very big difference between the competency of these rocks and the pink ones that we find from the Aswan quarry. But let's look at the diorites. I think the same thing applies here to the diorites. The younger ones from Aswan seem to be the unstable ones, and the more stable ones seem to come from the Eastern Desert. Now, again, however these were weathered, these seem to be falling apart. Look at the rear end of the Sphinx. They are eroding extremely badly. Now, these are the ones that I think came from the Eastern Desert, and I don't know whether these are a black granite or a more competent diorite. They could be named wrong, but this is the one that Brian showed, that Christopher Dunn did with his symmetry. Look at the lack of weathering on this thing. This is just beautiful. This one is at the Ramesseum. The weathering that's on there is not weathering, that is mechanically done. That nose and things were done deliberately. Now let's look at the basalt. Basalt is the basalt up here by Cairo is all fault related. The fault comes down here, and way down here is where in Bahariya in the Black Desert, here is one of the volcanoes, and look at all of the columnar jointing at the top of that volcano. They're just very, very small volcanoes. And like I said at the beginning, that stuff is mostly kind of oozy type lava, not an explosive type of lava. Now, the basalt I see, and I think it might be because of the columnar jointing, it seems to be in smaller blocks, and it's used a lot for some statues and things. But here's the flooring it's used for on the eastern side of the pyramid. This is flooring at Abu Sir, more basalt on the floor. And we passed this today. It's at just beside the step pyramid. This is the flooring at the eastern side of the pyramid of Userkaf at Saqqara. Now, let's change the subject here now that we kind of know what rocks we're looking at. How hard is it? And I get this asked all the time. A rock is only as hard as the minerals that make up that particular rock. The strength of the rock is a different matter. Those are two different things. Now, the naming of the rock is important because it gives you some idea of the minerals that the rock is composed of. The constituents of the rock must be known. And by that I mean the actual minerals, not the overall chemical composition. Here's the difference between the actual minerals and the chemical composition. And here for the silica, for example, all of these contain some silica. We had a friend who used to take pieces home and get them analyzed by a chemist back in the States. He'd come back with, oh, there's calcite in here, it must be limestone, when actually it was part of a feldspar. So you have to know what these the mineral composition is. So back to how hard is the rock? Let's have a look. Here is a granite. Specifically, it's a pegmatite, which is a coarse-grained intrusive rock with exceptionally large crystals. Now, here's your Mohs scale of hardness. We have a little tiny bit of quartz in here at a 7. We have a little tiny bit of feldspar in here at a 6. And this is all mica. It's a 3. This is a granite. How hard do you think that is? That is probably only a 3. Here's the next granite. This is the deep rose cyanide. And it has a minor bit of quartz, which would put a little tiny bit of 7 here, but most of it is feldspar and a small amount of pyroxene and amphibole. It's a solid 6. That is a hard, competent rock. We don't need it up higher than 6. 6 is a very hard rock. Now, here is a basalt. This is in India. It's mainly feldspar and pyroxene, would put it all at 6. But look at these green things up here. That's malachite. Those were gas bubbles, and malachite precipitated out along the gas bubbles. If these grow to any notable size, then the malachite is a hardness of 4. That will reduce your hardness. But that is only how hard they are. How strong are they? The strength of the rock depends more on how the mineral components are held together than the composition. Granite derives its strength from how tightly the crystal structure is held together. Sandstone and limestone derive their strength from how tightly the individual grains are held together. Now, granites are crystalline rocks. The minerals crystallize together. Sedimentary rocks are mechanically formed and held together by a natural cement, not crystallization. But for this, I will be considering them both together because it's much simpler to consider them both together. So we're going to learn a little bit about porosity, permeability, and cementation. So don't roll your eyes. This is really important stuff. Almost every rock has a type of natural cement to hold it together. If a rock is not well cemented, it will weather quickly and fall apart. Cement in a rock is a natural mineral component. This is a thin section. These are quartz grains in here. So this is a sandstone, and this is calcite cement in the middle of it. So this is what the cement in a rock would look like. Now, a well-cemented rock is a strong rock. Here's a well-cemented granite and a well-cemented sandstone. They're very strong. Here's a poorly cemented granite and a poorly cemented sandstone. You can see the difference. The one holds together and the other one does not. So let's start with a little bit of porosity. Now, porosity is the measurable void space between structural material. Here's a jar of marbles. All of this interstitial space between them is your porosity. Again, in between here is porosity. If you add something a different size, shape, it will reduce your porosity, but you still will have porosity in there. Here's just another picture of it, and here with porosity completely gone. Now, permeability. Permeability is a measure of how liquids flow through a medium with porosity. Here are your quartz grains again. This is your porosity in here. And look at how the arrow will flow through here. That is permeability. Trying to go through here, it will not go through here. That is impermeable. But overall, you have got a lot of porosity in here. So the diagram will show you this is a non-porous, non-permeable rock. This, because nothing can flow through there, it's porous and non-permeable. And here is porous with permeability. Now, the cementation. A natural cementation is a chemical precipitation formed within existing porosity and is regulated by the amount of permeability that is present. Cementation will alter both porosity and permeability. Here is a rock that is 100% cemented Look at how it looks like it should be hard and strong. Look at this. It only has a little bit of cement in here. That is probably going to weather and crush fairly easily. Now, cements are mineral cements, and depending on the mineral hardness, the cement will make the rock harder. So in that case, if you've got a quartz cement and quartz grains, that'll be hard. If you have calcite cement in there, that is not going to be as hard. So that's something people don't usually consider when they're looking at a rock. So if all the components are quartz, for this one, a quartz grains and quartz in here, that is going to be hardness of 7. But this one, this one is going to be much, much weaker. So why is this so important? Well, the cements give the rocks their strength. Without cements, the rocks will have very little strength. With uneven cementation, the rocks will weather unevenly. Now, for example, here's one in the Osirian. This is the sandstone wall behind here. This sandstone is cemented with a quartz cement. This is very hard. This is a hardness of 7 all the way through. Look at how unweathered this is. It's the same hardness as the granites in here. This is a very competent rock. This one, conversely, this is a quartz grain, but it's got cement. It's got a variable cement content, mostly calcite cement. So you can see it is weathering out unevenly. Look at the sand down here below. It's all falling out of this rock. So, because of the calcite cement in there, it is just not very, very hard or competent. You can get uneven cementation, and where you get these ridges, that is a harder cement in there. Where you get through here, it's a softer cement. So where you've got a softer cement, it is going to weather out. So for a good example, here is the Sphinx. We were there yesterday. The Sphinx displays uneven cementation. Overall, the composition of limestone, it's only 3. It's got uneven calcite cement, which is a 3 as well. So where you get the cement, you get these larger ridges. Where you don't get the cement, it is weathering out even more. So overall, the Sphinx is not very hard and not very strong. Now, here's a basalt cliff in Iceland. This is hard and it is strong. Here's a limestone beach in the Turks and Caicos. It is not very hard and not very strong. It's made out of the limestone. Now, here's a deep rose granite again in the King's Chamber. That is hard and it is strong. The pink granite obelisk at Karnak, it's hard, but it lacks strength. Same with this pink granite boulder by Aswan. It's hard and it lacks strength. So they are falling apart. Now, here's the side of the bent pyramid. The limestone blocks, they show these are all nummulites that are being dissolutioned out. It's limestone, hardness of 3, so it's not very hard and it's not very strong. Hopefully you're getting where I'm coming from there. We can't just say because it's a granite, it is hard. We can't just say because it's a sandstone, it's soft, because we can get some very hard sandstones. Now, rocks have sound, and it seems to baffle some people why rocks have sound. One of my main tools I use as a geologist is a set of pliers. I'm always whacking it on a piece of rock. I can tell the porosity permeability on a rock by banging it against a pair of pliers. All rocks emit a sound when struck with another object, my pliers. Low porosity and low permeability rocks will emit a high-pitched ringing sound. These are very tight rocks. High porosity and high permeability rocks will emit a low-pitch hollow sound. These are not tight rocks. And back to this. If this is cemented, the quartz grains, the quartz cement, this is no porosity, no permeability. It will ring like a bell. As opposed to this, with the quartz grains, even a bit of quartz cement in here, it will ring from a variable from a hollow sound to a moderate ringing, depending on the percentage and the type of its cements that are in there. Brian showed a picture of this. This is an obelisk at Karnak. And we used to be able to walk over the rope here, and you'd hit it with the palm of your hand and you could make it ring. It was not ringing like a bell. It was ringing, but it is not, it's strong, but it still is not as strong as it could be. We can't do that anymore, so they've uprighted the thing. Now, here's another case of it. Here is the ringing of these rocks. It depends on, again, the porosity, permeability, and the cementation. And also, they have cut these to size to make them ring in actual notes. This was in Hampi, India. Patricia and I went there a few years ago. But this was just quite astounding because each of these columns had a different degree of cementation and the cement, but also along these poles had different cements in them as well. So we had a fellow who played those. They could, each one of them, he would play a different tone, but up and down those columns, he could play a different note up and down them. And that is from porosity, permeability, and cementation. It's not magic. What's magic is that they figured that out. Now on to vibration of rocks. Sound is a vibration whose frequency is audible to the average human. There are other vibrations that are not at a frequency that is audible to the average human. Each rock will vibrate with a different frequency depending on its porosity, permeability, and cementation. In science, the vibration of the rock is used to map rocks underground in geophysical surveys. The vibration can also be used to monitor earthquakes. We've talked about the seismic before. This is just to reiterate it. This will pick up the vibrations. This too, some people will say they can hear the earthquake, but when you cannot hear it, this is an earthquake early warning system that will pick up the vibrations. Rocks vibrate. The vibrations can also be used in medicine and healing. People throughout time have used crystals and vibrations for diagnostic and healing purposes. In modern times, we use vibrations as well. For example, ultrasound. It's an imaging test that uses high-frequency sound waves to image organs and structures of the body. We were here today. This is at Saqqara, the healing hospital. This is a Turral limestone. It is just very, very competent rock. It's very fine, and it will just bounce waves off of it. Again, in the King's Chamber, and this is the what I think is the Eastern Desert granite, and especially with the baffles above here, and I think we discussed this out on the plateau the other day, that the vibrations will rise up and be forced back down on you. That creates just amazing, amazing vibration. This doesn't necessarily, this is in the Red Pyramid. This is a corbelled roof, and this was not necessarily made for vibration. It was used for spanning a void space, but it amplifies vibration. So it is just beautiful in there. But we'll quickly, we're going to switch to the colors of rocks. Rocks have different colors. They're very colorful things. The color is dependent on both the mineral components of a rock as well as the color of the cement. Most sand grains are in the beige, tan to gray hues. Limestones are similar colors with a more white tone. Here's a white sand beach, and it's composed of white limestone grains. This is in the Turks and Caicos. Here's a black sand beach, and it's composed of black sand grains from columnar basalt in Iceland. This is in Petra in Jordan. These are just amazing. This is all from, the red is from a red iron oxide, and the yellow is from a reducing iron oxide. These are just amazing in color. These are all from the cements within the rocks. This one, this is a Moki marble. This is, they always have said that the only place you find Moki marbles are in Utah and on Mars. But we find these on the dock at Aswan all the time. Anyway, the black on the outside of this is from a black iron oxide or black hematite, and the center is a red iron oxide, a red hematite. And they're really cool. Now, here is a hoodoo. This is not too far from where I live too. The cap rock has calcite cement in it, which makes it harder. That's why the hoodoos will have a big cap rock on it, and the underneath it will be eroding away. But all of the orange in here is an iron oxide as well. And for interest's sake, these are eroding at a rate of 1 centimeter per year. Now, this is in China, and I don't know whether this is an AI manufacture, but every picture I saw looked like that, and I thought, this is a really cool picture. I'll just put it up. But I am going to, because we're going to have to get ready for our next one, I'm going to stop there for today. And here is a hot spring monkey from Nagano, Japan saying, see you tomorrow for part 2.
Porosity, permeability, and the cementing being significant for vibration. Is the mineral content irrelevant to vibration?
Well, the minerals will have a hardness. So if you've got calcite in there, it's not going to be as hard as a quartz cement. So if you've got calcite cement, it'll ring, but it's not going to be as, like for the actual mineral, I don't know the characteristics of like a crystal, but in the cement, it won't ring as nicely as, say, a quartz cement. Is that?
But you're saying you're looking much more at the cement than what is being cemented.
Well, what's being cemented does play a part in it too. It all kind of plays a part.
Thank you.
We can try and find bits and pieces along the way and test out the theory.